Now we're ready to talk about forces. A force is merely just a push or a pull capable of changing an object's state of motion. In other words, just a push or a pull that moves an object. That's really what a force is. When we talk about forces, we do like to look at each individual force. However, with the overall effect on an object isn't going to be determined by the individual force, but by the sum of all forces. In other words, the net force on an object. Let's take an example of this battleship here. Let's say it's moving to the east the propellers pushing the battleship with a force of 1,000 units to the east. The wind is also at its back, pushing it along at 1,000 units to the east. Well, the motion isn't going to be affected by the propeller alone, nor is it going to be affected by the wind alone. It's going to be affected by both of them together. So when you add these two forces together, you get a net force of 2,000 units to the east. Let's take the second example. The battleship is still pushing to the east with a force of 1,000 units, but now the wind is going to be pushing the other direction with a force of 1,000 units to the west. Now each force is pushing that battleship, but the net motion is going to be zero because these two forces cancel each other out because they are in opposite directions. This final example, the battleship is still moving to the east with propellers pushing at a force of 1,000 units, but the wind, in this case, is going to the west with a force of 2,000 units. So what will be the net motion? The net motion of this battleship will be determined by the total, which would be 1,000 units to the west. Now, here are some of the fundamental forces that we're going to deal with in this course. The first is gravitational forces, the interaction between masses. This determines the motion of planets, the stars, the galaxies. It also determines, it doesn't determine solely, but it is a large part of our motion here on the surface of the Earth. Electromagnetic forces are the interactions between electric charges. This has to do with both electricity and magnetism, and has to do with the orientation and setup of different atoms and molecules in chemistry. Now we're going to have an entire chapter on electricity and magnetism coming up here a couple chapters from now, chapter 6. A couple other forces include what's called the weak force. It's involved in certain nuclear reactions. Then you also have what's called the strong force, which is the force that binds and holds the nucleus of an atom together. The third and fourth forces, weak and strong forces, those will come up every once in a while through the course, but the forces we'll primarily see are gravitational and electromagnetic forces. All right, let's take a look at motion based on forces. Now, note that motion will continue unchanged if all the forces are balanced. Remember the battleship example that we saw before? If all the forces balance to zero, there's no net force, therefore your motion remains unchanged. So to illustrate this, you have a satellite going around the Earth, or satellite going through space, we'll say. It's going to have constant velocity. There is going to be absolutely no force on that satellite, so the motion remains unchanged. Now, if we have what's called a retarding force, that would be a force opposite the direction of motion. That's going to slow down the object that is moving. But if you have a force that's in the same direction as motion, then that's going to actually increase the speed of that object. Then finally, if you have an object that's moving, but a force pushes it in a different direction, say the satellite's going to the east and we have a force pushing it to the north, then that's when we get a change in direction. So the result is you can have either changes in speed or direction or both. due to forces. So now we come to the three laws of motion. These were first detailed by Sir Isaac Newton. Now, everyone knows these three laws, and maybe we don't always remember them, but everyone's heard them at some point in their life. The thing that's not as well known is that these three laws were not only described, but described mathematically by Isaac Newton as he developed the field of calculus. Calculus was invented to describe motion. And of course, one of his big purposes in doing this was to describe the law of gravitation. So next time you start thinking about mathematics, algebra, and calculus, remember that this field of mathematics was created, or developed, I should say, to describe motion and physics. Now, the basic idea of this calculus to describe forces and motion. Okay, here is Newton's first law, also known as the law of inertia. Simply stated, every object remains at rest or in its state of uniform straight line motion unless acted upon by an unbalanced force. Perhaps you've heard it this way: an object in motion stays in motion, or an object at rest stays at rest unless acted upon by an outside force. Basically, what that means is whatever an object is doing, it's going to keep doing that unless a force changes it. This is inertia. The inertia resists any changes of motion. So here's a good example of this. Let's say that you're sitting on a bus. You're sitting frictionless in a bus, which means you can slide around easily. And then the bus starts moving forward. Well, because you're on a frictionless surface, you're not going to move. The bus will start moving, but it's going to appear that you slide backwards. But really, you're just staying in place while the bus moves forward underneath you. Now, if we take that one step further, let's take this bus, and let's say that you are now moving with the bus. So you have the same velocity as the bus, but then the bus turns. Since you're on a frictionless surface, you're going to keep moving straight until the bus's wall hits you and then starts pushing you to the side. So in other words, Newton's first law, you are going to stay in motion, but then you had an outside force, the force of the bus pushing you inward, which is needed to overcome inertia and change your direction. This force of the bus pushing on you is what we call a normal force. It is often mistaken for something we call a centrifugal force, which is a push outside. That's what you would be feeling here. Really, there's no such thing as a centrifugal force. All it is inertia pushing you forward, and you're feeling that inertia wanting to move you into a straight line, but the normal force is changing your direction instead. That's really what you're feeling. There, sorry, that was just a bit of a side tangent. Thought I'd address it here for you. Newton's second law basically indicates that forces cause accelerations. In other words, force is proportional to acceleration. The harder you push, the faster it will accelerate. Now, they're proportional, but that doesn't mean they're equal. You need what's called a proportionality constant, which creates this perfect relationship between force and acceleration. That proportionality constant is what we refer to as mass. So force is equal to mass times acceleration, F equals ma. This is perhaps one of the two or three most well-known equations in all of physics. Basically what it says is the more force you have, the more acceleration you have. But the more mass you have, the less acceleration you have. Put into terms we've already talked about, force and acceleration are directly proportional, but mass and acceleration are inversely proportional. When we measure forces, we say that we use the unit of a Newton, named after Sir Isaac Newton, who was so phenomenal in the field of forces. So a force might have something of, say, 10 newtons. Now, when talking about Newton's second law, we need to come back to a point we made earlier, and that is we're not worried about individual forces. They are all important, but really we're worried about the net force. So here's an example of a biker that is pushing forward. I want you to notice in this example that the net force here is 0. The biker is pushing forward with some force F applied, and he's being resisted by air resistance, which is pushing him backward, and friction, which is also pushing him backward. And so the force of air resistance plus the force of friction is going to have the same magnitude but opposite direction as the applied force, which tells us that the net force is 0. Here, this is an error from the publisher. This should say net force, F net. The net force is equal to 0. Now, if your net force is equal to 0, then F equals ma, 0 is equal to ma, then that means that we have 0 acceleration. And if there is no acceleration, then that means that we have to be moving at a constant velocity. Reason for this being, what is acceleration? Recall from earlier that acceleration is a change in velocity over time. But if there's no acceleration, then there has to be no change in velocity. Therefore, velocity is constant. Newton's third and final law of motion states, talks about a relationship between forces of objects. Whenever two objects interact, the force exerted on one object is equal in size and opposite in direction to the force exerted on the other object. Perhaps you've heard it more commonly as, to every action, there's an equal and opposite reaction. Basically, that means when an object exerts a force on an object, when object A exerts a force on object B, then object B is going to exert an equal but opposite force on object A, meaning same magnitude, same strength, but opposite direction. So let's consider a simple example of, say, a game of football. You have an offensive lineman who is protecting the quarterback from the defensive tackles. Okay, so the quarterback says hike, and all of a sudden these two people from opposite teams push against each other, and they end up in a standstill. They're not moving. Well, the offensive lineman is pushing the defensive tackle, and they're pushing each other with equal but opposite forces. The lineman is pushing the tackle, but the tackle is pushing the lineman, equal and opposite. And so since they are equal, the net force is going to be 0. They don't move. Here's another great example of Newton's third law, and that has to do with rocketry. When a rocket is launched out into space, the thrust of the rocket pushes out of the rocket. Well, since it's pushing on the air underneath it, well, what does the air do? The air pushes back, and that is what actually lifts a rocket up into the air.